Bringing thousands of tons of rolling mass to a safe, controlled halt is a massive problem of physical momentum. Stopping that weight uniformly requires mechanical braking force applied across rakes that routinely exceed 50 wagons, demanding fail-safe redundancy across a train stretching over a kilometer long. Indian Railways achieves this using a single-pipe graduated-release air brake system. The architecture relies on a paradox, using one continuous pipeline to supply heavy mechanical power and transmit delicate control signals simultaneously. A pressure reduction from the driver propagates down this line, forcing every wagon to apply braking force uniformly across the train. This pocketbook excerpt outlines the system's explicit advantages: shorter braking distances, higher braking force, and significantly reduced brake power deterioration compared to older mechanical systems. The margin between a highly efficient heavy-haul network and a catastrophic failure lies entirely in mastering this dual-function pneumatic logic. To understand how the system executes a stop, we have to build the pneumatic circuit on a single wagon, starting from the mechanical output and working backward. This section of the Freight Handbook details the terminal component, the brake cylinder. Its sole purpose is to convert pneumatic energy into the mechanical braking force that drives the brake blocks against the wheels. Pushing that cylinder requires a localized power source, a high-pressure air tank called the auxiliary reservoir. Feeding it is the brake pipe, a continuous supply line running the train's length, connected by open cutoff angle pocks parallel to the pipe. Because the system operates in harsh environments, a dirt collector sits at the junction, using centrifugal action to strip dust and foreign matter from the air before it reaches the internal components. At the center of this circuit sits the distributor valve. It acts as the logic gate, intelligently routing air between the brake pipe, the auxiliary reservoir, the control reservoir, and the brake cylinder. During the initial charging stage, the locomotive compressor pressurizes the continuous brake pipe to a strict baseline of 5.0 kilograms per square centimeter. As the brake pipe reaches 5.0, the distributor valve routes that air inward, charging both the auxiliary reservoir and the control reservoir until they equal that exact 5.0 pressure. Simultaneously, the distributor valve vents any remaining air in the brake cylinder to the atmosphere, guaranteeing the mechanical brakes remain fully released. This fully charged state creates a delicate pneumatic equilibrium. The local reservoirs are loaded, the cylinder is clear, and the fail-safe trap is set, waiting for a drop in brake pipe pressure. The fail-safe trigger fires when the driver deliberately vents air through the locomotive's brake valve, dropping the brake pipe pressure below the 5.0 baseline. Step 1, the localized pressure drop reaches the distributor valve. Because the control reservoir is still sitting at 5.0, a pressure differential forms inside the valve body. Step 2, the distributor valve reacts mechanically, disconnecting the control reservoir to isolate it as a constant reference. Step 3, the valve opens a direct pathway, sending air from the fully charged auxiliary reservoir into the empty brake cylinder. Step 4, high-pressure air rushes in, driving the piston outward and transmitting massive mechanical force through the rigging straight to the wheels. The brilliance of this design is proportionality. The physical braking force applied by the cylinder perfectly matches the exact pressure reduction in the brake pipe. Looking at this single wagon test pro forma, we see the numerical peak of this response. A full-service application caps the brake cylinder pressure at precisely 3.8, plus or minus 0.1 kilograms per square centimeter. To ensure this pneumatic pressure translates correctly, mechanical checks mandate strict piston stroke limits, 85 millimeters for empty wagons and 130 millimeters for loaded ones, with a 10 millimeter tolerance. This proportional chain reaction converts a slight air reduction commanded from the cab into thousands of tons of synchronized stopping power across the train. To release the brakes, the locomotive compressor restores the brake pipe pressure to the 5.0 baseline. The distributor valve reads the pressure rise, isolates the auxiliary reservoir, and opens an exhaust port to vent the brake cylinder back to the atmosphere. A mechanical return spring then pulls the piston back to its resting position. A complete release is achieved as the brake pipe approaches 4.85 kilograms per square centimeter. Because this system dictates the safety of the train, the distributor valve must perfectly interpret pressure changes, governed by strict Chapter 7 testing limits. This table outlines the mandatory testing values. The sensitivity standard requires the valve to initiate braking if the brake pipe drops by 0.6 kilograms per square centimeter within a tight 6-second window. Conversely, the insensitivity standard demands the valve completely ignore a slow pressure drop of 0.3 kilograms per square centimeter stretched over 60 seconds. These exact margins allow the logic gate to obey rapid, intentional brake commands while safely ignoring the slow, harmless microleaks inevitable in a long train. Moving from theoretical design to real-world application, field engineers use these precise parameters to isolate faults out on the track. The primary diagnostic tool is the brake continuity test. This is mandatory whenever a locomotive is attached or the rake configuration is altered. The test verifies that pressure destruction initiated at the rear angle cock is perfectly and immediately mirrored on the driver's gauge at the very front of the train. Once continuity is confirmed, the target metric for a long train requires rebuilding pressure to 5.0 in the locomotive and achieving at least 4.7 at the rear brake fan. If a driver experiences unexpectedly low brake pipe pressure en route, they execute the leakage test. According to this pocketbook procedure, the engineer reduces pressure to 4.0, isolates the valve, and waits. The strict threshold is that the pressure drop must not exceed 1.25 kilograms per square centimeter over a 5-minute window. Deviations from these baseline metrics point directly to specific physical defects in the system. This troubleshooting table maps common defects. Brake binding is frequently traced to a disturbed empty load device or partially applied handbrakes. By contrast, poor brake power is usually caused by a closed angle cock, braking pipe continuity, severing communication to the rear wagons. The ultimate safety of the operation relies entirely on human discipline, ensuring every angle cock, hose couplin, and pressure reading adheres strictly to numerical tolerances. From a controlled air release in the cab to the massive friction halting thousands of tons of steel, the single-pipe air brake system works because it relies on an uncompromising mathematical relationship between pneumatic logic and mechanical force.